Welcome to this deep dive into, well, a really fascinating corner of mathematics. Today, we're venturing into the Online Encyclopedia of Integer Sequences, the OEIS. It's such a vital resource if you're exploring number theory. Think of it maybe as a meticulously curated map of numerical patterns. Our focus today is sequence A000225.
Yes, the OEIS. It's truly a remarkable collaborative effort, isn't it? A place where, seemingly disparate mathematical ideas often, well, they converge. And A000225 is a prime example, really. It's a sequence that just pops up in some very surprising places.
It really does.
Yeah.
So for those of you maybe with the OEIS open, you'll see A000225 is defined by this quite elegant formula, AN equals 2n1. That gives us the sequence 0, 1, 3, 7, 15, laid, and well, so on. Interestingly, it's also sometimes called Mersenne numbers, though usually that term's more reserved for A001348. So what's the sort of initial spark, the first thing you notice when you look at this sequence?
Well, the first thing that strikes you, I think, is the fundamental relationship with powers of 2. Each term is just 1 less than a power of 2, second minus 1. And this simple connection, it unlocks a really powerful visual understanding through binary representation.
Ah, yes, the binary connection. Right. Here's where it starts to feel, well, really fundamental. Can you elaborate on that a bit?
Absolutely. Take any term in the sequence, say 7. It's 2 cubed minus 1. Now, if you look at its binary form, 1, 11, 3 ones, or consider 15, and that's 2 to the power of 4 minus 1, its binary is 11, 11, 4 ones. It's quite a direct mapping. The nth term, an, is simply a number represented by n ones in binary, which makes it incredibly relevant in computer science where binary is just the bedrock.
That's such a clear and immediate link, yeah.
Mm-hmm.
Now, looking at the OEIS entry, it reveals the sequence isn't just a binary curiosity. It has some pretty fascinating interpretations in combinatorics, starting with subsets.
Yes, that combinatorial interpretation regarding subsets is, well, it's quite beautiful. If you have a set containing, say, n distinct elements, the total number of subsets you can possibly form is 2 to the power of n. Now, if we exclude just one of those subsets, the empty set, the one with nothing in it, we're left with exactly 2n1 non-empty subsets. That's precisely an.
Right.
So, for example, if you have a set with 3 elements, a, b, c, it has 2 cubed, which is 8 total subsets. Remove the empty set, and you're left with 7, and that's a 3. It's a direct consequence of how power sets work.
That's a lovely connection. It really is. Then the OEIS introduces another one, maybe a slightly more intricate combinatorial view involving pairs of subsets. This one took me a moment to fully get my head around.
Yes. It's intriguing. What's intriguing here is the interpretation of an plus 1. Counts the number of pairs of subsets, let's call them x and y, that you can pick from the power set of a set A that has n elements. But there are 2 specific conditions. First, x and y must be disjoint. They can't share any elements. And second, either x has to be a subset of y or y has to be a subset of x.
Okay. That's quite a mouthful. Is there a more maybe intuitive way to picture this?
There is, thankfully.
Yeah.
The OEIS points out a simpler equivalent condition which helps a lot. It's the number of pairs, x, y, where at least one of x or y is the empty set.
Oh, okay.
Let's think about why this works. If one of the sets is the empty set, then they are automatically disjoint, right? And the subset condition is trivially true because the empty set is a subset of everything. So if you have an n-element set, its power set has 2n elements, 2n possible subsets. If we choose the empty set as our first element, x, we have 2n possibilities for the second element, y. Now, if we pick any of the 2n subsets as the first element, x, we have only one choice for the second element, y, to satisfy this simplified condition, the empty set. But hang on. We've counted the case where both x and y are the empty set twice.
Ah, right. Double counted.
Exactly. So your 2n possibilities plus another 2n possibilities minus the one we double counted. That gives us 2n plus 2n1, which simplifies nicely to 2n1, or 2n plus 1, 1. And that, of course, is an plus 1.
That simpler explanation really does clarify it. Okay. Now, shifting gears just slightly, the OEIS mentions a connection to Gaussian binomial coefficients. For our listeners who might be diving into more advanced number theory, what's the significance of that particular link?
Well, the fact that an is the Gaussian binomial coefficient, often written n, 1q, with the parameter q set specifically to 2, it provides a fascinating bridge, connects to catalogs and combinatorics. You can think of Gaussian binomial coefficients as a sort of generalization of standard binomial coefficients, but they incorporate this variable, q. When q takes the specific value of 2, this more general structure collapses precisely down to our familiar 2 and 1. It really highlights how this sequence isn't just some isolated phenomenon, but actually fits within these broader frameworks in combinatorial algebra.
It's amazing, isn't it, how this seemingly simple sequence turns out to be just a specific instance of these more abstract concepts. Now, for something maybe a bit more tangible, the Tower of Hanoi puzzle, it seems our sequence plays a starring role there, too.
It does indeed. A classic. The minimum number of moves required to solve the standard Tower of Hanoi puzzle with n disks. It's exactly an equal 2n1. Think about the puzzle with just 2 disks. You need 3 moves, right? Move the small disk, move the large disk, then move the small disk back on top.
3 moves.
And a2 is indeed 2 squared minus 1, which equals 3. It's a really beautiful demonstration of the exponential growth that's just inherent in the problem's recursive structure.
That's a perfect concrete example. Yeah, the OEIS also points out that our sequence A000225 is just one member of a larger family.
Precisely. The formula an2n1 is, you could say, a specific case of the more general form, an1, a1, where a is some integer greater than or equal to 2. Our sequence is just the case where a equals 2. And the OEIS helpfully cross-references related sequences for other values of a, like A003462 for A3, or A002450 for 4, and so on. This shows how A000225 sits within a broader landscape of sequences with similar underlying multiplicative structures.
It's like seeing the template, yeah, for a whole family of sequences. Now let's look at another seemingly unrelated area, Pascal's triangle.
Yes, another elegant connection there. So the sum of the elements in the nth row of Pascal's triangle, if we start counting from n0 at the top one, is 2 to the power of n. Consequently, if you sum up all the elements in a Pascal's triangle down to the nth row, so including row 0 up to n1, the total sum is 2n1. Which is our sequence, A. And again, it's a nice interplay between binomial coefficients and powers of 2.
The connections just keep unfolding. It's quite remarkable how this basic formula keeps popping up in different mathematical domains.
Okay, so the OEIS then introduces Stirling numbers of the second kind. For our audience, what do those generally describe, and how do they tie into our sequence A000225?
Right, Stirling numbers of the second kind. They're usually denoted SM min k. Basically, they count the number of ways you can partition or divide up a set of n objects into exactly k non-empty, unordered subsets. The OEIS highlights that our sequence term an is equal to Sm plus 1, 2.
Okay, Sm plus 1, 2. Yes. So in simpler terms, 2n1 represents the number of ways you can divide a set containing n plus 1 elements into precisely 2 non-empty groups. The example given for n-pre is quite illustrative. We know A3 is 7, and S42 is also 7. It represents the 7 distinct ways you can split a 4-element set into 2 non-empty parts.
That provides a deeper understanding, of the combinatorial richness of this sequence. From subsets to partitions, these fundamental counting principles are really at play. And the OEIS keeps going. It mentions relevance to the frogs problem.
The frogs problem. Another classic puzzle. You typically have, say, n brown frogs and n green frogs on lily pads in a line, facing each other, with one empty pad in the middle. The goal is to get the brown frogs to where the green frogs started, and vice versa, following certain jumping rules. And the minimum number of moves required to interchange these n frogs on each side turns out to be, guess what? an equals 2n1.
Another puzzle neatly solved by our sequence. It's incredibly versatile. Then, venturing into graph theory, the OEIS states that an is the length of the longest path in an n-dimensional hypercube.
That's a fascinating link, connecting it to higher dimensional geometry. An n-dimensional hypercube, has 2 to the power of n vertices. Finding a path that visits every single vertex exactly once, that's called a Hamiltonian path, is possible in a hypercube. And the length of such a path, the number of edges it contains, is 2n1. Which is an. And sticking with graph theory for a moment, the sequence is also the diameter of the n-Hanoi graph. Could you maybe explain what that entails? Sure. The n-Hanoi graph is a way to visualize the Tower of Hanoi puzzle. Each node, or point, in the graph represents a possible configuration of the n disks on the pegs. An edge connects 2 nodes if you can get from one configuration to the other with a single valid move. Now, the diameter of this graph is the longest, shortest path between any 2 possible states, any 2 configurations of the puzzle. And remarkably, this longest, shortest path has a length of an equal to 2n1. It again underscores the fundamental role this sequence plays in understanding the complexity, the structure of that puzzle.
It's all interconnected in such a beautiful way. Finally, the OEIS gives us a glimpse into the various formulas that can generate this sequence, including some recurrence relations.
Yes, absolutely. There are multiple ways to define and generate this sequence, which is often true for fundamental sequences. A very simple recurrence relation is an plus 1 equals 2 an plus 1, starting with the base case A00. This shows very directly how each term is built just from the previous one. Double the previous term and add 1. Another fundamental way to express it, which we touched upon earlier, is as the sum of a geometric series, an, is the sum from k0 up to n-1 of 2 to the power of k, which, as we know from the formula for geometric sums, simplifies exactly to 2 and 1. These different formulations offer, valuable perspectives on the sequence's underlying structure.
This has been a truly illuminating journey through the many facets of A000225. Just amazing. So to maybe summarize, what are the key insights about this sequence for our listeners?
I think the main takeaway is that the sequence an equals 2n1 is far more than just a simple numerical pattern you might write down. Its appearance in areas ranging from, basic binary representation and counting subsets, all the way to the complexities of the Tower of Hanoi puzzle, the structure of hypercubes, and even Stirling numbers. It reveals a really fundamental mathematical motif. Its prevalence, really, it underscores the deep and often surprising connections that exist between seemingly disparate branches of mathematics.
Absolutely. And for our listeners, particularly those maybe using the OEIS as number theory students, understanding A000225 provides such a crucial stepping stone, doesn't it, for exploring related sequences, as the OEIS itself often suggests, looking at things like Mersenne primes, that's A000668, or the Mersenne exponents, A000043, that will build directly upon this foundation we've discussed.
Most likely. This sequence, A000225, it acts as a kind of Rosetta Stone, you could say. It helps you decipher the language of other integer sequences and understand their underlying relationships much better.
So as you continue your own exploration of the OEIS, maybe consider this. Given the surprisingly diverse interpretations of this one sequence, 2 and 1, like what other seemingly unrelated mathematical concepts might be connected by similar fundamental number patterns? It's a question that really highlights the interconnectedness and, frankly, the beauty of mathematics. Thank you for joining us for this deep dive.